Welcome to part 2 of my video about my kitchen timer. If you already saw my first video, then you know what this is about. If you haven't seen my first video on this, I suggest clicking on the link to go watch the video, and you'll get a nice demonstration of what this is all about. It's a kitchen timer made out of Cold War era Nixie tubes. Now, before I launch into my project and how I designed it, what tools I used, and so forth, I'll just give a quick rundown on what Nixie tubes are all about. Roughly around the 1960s to 1970s, Nixie tubes, which they're a form of a digital display that show numbers, characters in some cases too. They were the only economically feasible display that you could design into your laboratory test equipment. Nixie tubes were predominantly found only in laboratory test equipment, things like digital multimeters and frequency counters, where that's where you would find Nixie tubes. Eventually, they fell out of favor because LCD and LED took over. They're just better. They're more reliable. Somewhere along the line, hobbyists began using Nixie tubes in their projects. This eventually led to cool projects that were driven by microcontrollers, and people made clocks out of them. Right around 2005, 2006, people then began to incorporate the GPS signal to keep time. So now you have Nixie clocks that you can purchase or build yourself using GPS accuracy, and that's pretty cool. So that's pretty much what a Nixie clock or what a Nixie tube is and how I got into it, what I knew about it before I started. So, on a whim, I decided to go on eBay and purchase Nixie tubes. I got this box, and I couldn't wait to open up the box. Inside, I found 6 Russian Nixie tubes, model IN-18. Those are one of the larger ones. I couldn't wait to turn them on, but before I did that, I had to actually go out and purchase a power supply. Now, rather than build a switcher or something like that, I just went and got a variac and bridge rectifier and capacitor to build a little DC source that I could vary the voltage quite easily. So I used that and I turned on the Nixie tubes and verified all the digits were working and everything. I thought it just looked so cool. And they came with this data sheet showing everything's in Russian. The only thing I understood were the Arabic numbers and the little diagram showing the pinout. And I took the pictures and I sent them to my friends and all that. It wasn't very long before I decided to build a little circuit on a solderless breadboard using a microcontroller and a driver, just so that I could see the display working and changing digits rather than just a power supply connected to it. And you can see here the circuit running, the very first circuit running. All it did was it counted, and I could see the tube advance. And that was really all that I wanted at that moment in time. The IC chip that I'm using to drive the Nixie tube is made by Supertex Incorporated. It's a 32-bit channel serial to parallel converter. So 32 bits on the serial input converts to 32 bits parallel on the output. On the output are these high voltage FETs that provide the ground for the cathodes. The cathodes are the digits of the display. It's a really cool chip. I really like it. It enabled me to quite easily incorporate a pulse width modulation to get a nice looking fade between digits on the tube. I didn't find this chip myself. I found it on the internet. So if you just Google drivers for Nixie tubes, this chip or something close to it will pop up as one of the search results. About the PC board that you see on your screen, that was something that I made with a Dremel tool, and I stuck the IC on the PC board using two-sided sticky tape, foam sticky tape. And then I used very fine uh, enamel covered copper wire. I think it was something between 40 to 44 gauge enameled wire. And I just kind of used my soldering iron to burn off the insulation and then solder it simultaneously to the chip leads and then to the makeshift pads that I had uh, routed out using the Dremel tool. Now, uh, you can buy boards off the internet to mount the chip on properly and all that, and even have leads to plug into your solderless breadboard. But at that moment in time, I was just so enthusiastic that I just had to do it. I had to just mount this IC. I had to connect the IC, and I had to just do it. So I made this kind of weird adapter board I guess this is a QFN package, to convert the QFN package to something that would work on the solderless breadboard and then the tube. It wasn't long before my enthusiasm led to using schematic capture and layout to design a proper PC board for this Nixie project. Now, right around that time when I decided to do this, I actually I had gotten to the point where I had a need for something. This is when I decided I needed a kitchen timer, and all of that came about because I was out in the backyard grilling chicken breast that I had marinated. And when you grill a chicken breast, the thing with chicken breast is you have to keep it moist, and that means you can't cook it for very long. So if you have it on a really hot grill, I've been, you got to do it real quick. So I've been doing 3 minutes per side. So I'd bring this kind of like a casserole dish out to the backyard, and then have a really big spatula for the grill. The grill's just blazing hot. I'd get the chicken on there, and it would have to be there 3 minutes, and then I have to flip the side, and another 3 minutes, and then get it off the grill real quick. Right? So what I would do is I would use my cell phone for the timer, uh, and that didn't work very well. First, the sun is really bright, so it's hard to see the display. Second, the display is constantly turning off because the cell phone is saving its battery. And then third, because I'm handling chicken and it's marinated chicken, it's moist, my fingers are moist, I've got liquid water, balsamic vinegar on my fingers, and that's getting on top of the cell phone display, shorting out the capacitive display, making the display not respond to my finger movements, all happening while I'm trying to do something quickly with the chicken, just cook it to, 3 minutes per side. Anyway, so that's what drove this. I was like, hey, you know what? I've been screwing around with these Nixie things and all that, and I, just no real plan. Why don't I make a kitchen timer? So that's how that started. So I grabbed Altium Designer. That's what I used to design it. Um, I have purchased Altium Designer. It was something that an employee of mine way back in 2010 used for my designs. Uh, as a microwave and RF engineer, the only type of CAD that I had ever used was AutoCAD for thin film design, and I used Cadence for IC design, for doing some layouts for IC designs. But I had never actually used any tool for a PC board because typically what I did didn't involve PC boards. But I got, after I had a project that I needed to get done with my business, and I had hired my previous employee as a contractor, and she did some PC boards for me. And during that process, I ended up learning how to do the PC boards myself. So I started using Altium. Then I bought Altium, and then my very first project was actually this Nixie clock, this Nixie timer. Uh, and I generated these PC boards here. So this is the very first PC board that I made. And then from there, I soldered up all the components and went through the normal process of bringing the board up and troubleshooting and modifying and all that, as well as writing the firmware and improving the firmware. And I did all this on my spare time. Here's a photograph of the countdown timer at a coffee shop in downtown San Jose. Uh, Here, I think, was when I got the both displays working. I had already written the firmware to have one display working. Then I needed to augment that to, for both of the displays going. So by this point, I had gotten the pulse width modulation for the fade going, and both rotary encoders working, and both displays working. So here you can see I'm adjusting it, and it's responding as it should. This was before I had wrote in the software interrupt for the 1 second intervals, which then you could use to get it exactly to 1 minute. But it all came in stages. One thing that I haven't mentioned just yet is what I used to write the firmware. I wrote the firmware using Microchip's IDE compiler called MPLab. So I wrote this in C, which is nice. I've written a few things in machine code using Microchip's compilers or assemblers, but this one is in C, which made things just nicer. Yeah, I really had to write everything for this. Just a lot of the things that the support you would need, debouncing the rotary encoders, and using the software interrupt that's based on an internal timer to have it keep time so that you have 1 minute intervals. Using the hardware interrupts so that when you spin the rotary encoder, the IC immediately jumps to a subroutine to then update the display and basically reset the counter to what it needs to count down from. And then there were the LEDs, which I've never really quite finished that. I just kind of wrote just enough to get the LEDs lit up with a few colors and all of that. But the LEDs are driven with these LED drivers that take a serial input and then they drive an RGB LED. In this video here, there's actually 8 of them there, and those particular chips are actually not in production, so I had to replace those. So there's already a version 2 of this board designed using those 8 chips got consolidated to 2 chips, and something that's in production. But anyway, that's not really that important. But yeah, I mean, it just all comes down to you put in all of these physical hardware bits, and then later on you write the firmware, and you kind of get to a point. I mean, there's so many things to do. You get to a point where you just tell yourself, well, I'll put all of these hooks in here, these hardware hooks in here, and I can write the firmware later. Coming from the point of view as an analog engineer, I can really see how the digital people are kind of pissed off, because that mindset of we'll build the hardware first, and the firmware that'll just come later at some point. Well, what really happens in the context of engineering schedules is all the people writing the firmware, they're at the very end of something. They're not at the knife edge of a project, really. At least not in the field that I've been in. Anyway, this was one of the most enjoyable things that I've ever done. I just felt like I had to make this video to show other people and to document it. So anyway, I hope you enjoyed it. I tried to keep it as short as I could, but it's already getting close to 15 minutes long. Anyway, thanks for watching.